This is Walter Cronkite for CBS Reports. It was mid-July 1962. Russia had just announced resumption of nuclear testing. Europe and the United States were watching the first international television via Telstar. The Senate had just voted to kill Medicare. Maury Wills had stolen his 48th base for the Los Angeles Dodgers. And most Americans were making plans for trips to the mountains, beach, or the ballpark. But other Americans were preparing for a voyage of another kind, and most of those vacationing Americans would be home long before this Voyager would reach its destination, the planet Venus, 36 million miles away. For this was man's second effort to reach his closest neighbor in the solar system, his longest journey on the new ocean of space. The Soviet Union had tried it the year before, but the Russian explorer, Venus 1, lost its radio voice 15 days out and was heard no more. Now it was the turn of Mariner, the 447-pound space traveler with 6 scientific experiments aboard. Experiments which would seek to solve the mysteries of Venus and provide information on the conditions in the deep reaches of space which man himself hopes to navigate. Launch time came in the darkness of early morning on July 22nd at Cape Canaveral, with tension heightened by the record of Soviet successes in orbiting men around the Earth. This was the opportunity to demonstrate again the superiority of American technology and instrumentation in probing deep space. The liftoff was perfect. In the first 3 minutes, Mariner was nearly out of sight. Then observers saw a distant flash in the dark sky. The range safety officer had pressed the destruct button, and the brief voyage of Mariner 1 was over. In the post-mortem that followed, the most unlikely culprit yet was assigned the blame. Mariner 1 and $18.5 million had to be aborted for the want of a hyphen in the control computer system. This piece of grammar should have been fed into the computer along with other guidance instructions. When it was not, the Atlas began to receive incorrect steering signals from the blockhouse systems and had to be destroyed. If the loss of time and money was great, the humiliation and damage to morale was as crushing. Mariner's appearance as a prize exhibit of U.S. space technology had been scheduled as a part of the first international television broadcast via Telstar to Europe. Now had to be canceled. But there was a backup program. Mariner originally had been designed as twins, and now Mariner 2, designed to follow its brother into space 1 month later, was coming up. The story of Mariner 2 and its 180 million mile journey to Venus, the hazards and near failures, its reports on the nature of deep space, and man's changing picture of this new dimension on which he is beginning to embark, is the subject of tonight's CBS Reports.
CBS Reports, 109 Days to Venus, is brought to you by Schulten. CBS Reports, 109 Days to Venus. Here now is CBS News correspondent Walter Cronkite.
That mariner of another day, Christopher Columbus, set sail from Spain on August 3rd, 1492, and sailed on and on at 4 miles an hour until he arrived in the New World 68 days later. Mariner 2 was launched from Cape Canaveral on August 27th, 1962, and cruising at 7,000 miles an hour, was scheduled to arrive at or near Venus 109.5 days later, 1/3 of an Earth year, a half of a Venus year. No life would be at stake with the voyage of Mariner 2, but the hopes and prayers and sweat of hundreds of dedicated engineers who built and launched her would be going with her. At 1:53 a.m. Eastern Daylight Time on the morning of August 27th in the year of 1962, Mariner 2 stood on the pad at Cape Canaveral, ready to leave planet Earth for planet Venus. But this Mariner was a different spacecraft than the one envisioned when the project began. The original Mariner design of 2 years before had contemplated a spacecraft weighing half a ton, which could carry a couple of 100 pounds of scientific instruments. But this was when it was thought that Centaur, our first liquid hydrogen rocket, would be ready as a second stage on Atlas. Centaur now is 2 years behind in development, and planetary orbits are inflexible. If Venus was to be observed before mid-1964, the reliable but less powerful Agena second stage would have to be used now to take the place of Centaur, and Jet Propulsion Laboratory would have to cut Mariner down almost 2/3 in weight to 447 pounds. And of that amount, only 41 pounds could be set aside for scientific sampling instruments. Of the 6 experiments aboard, 2 would gather information about Venus's atmosphere and surface temperature. Included also were instruments to collect cosmic dust, a solar plasma detector, charged particle detector, a magnetometer, several Geiger counters, and a small rocket motor designed to deliver 50 pounds of thrust at a critical time. Mariner was constructed to convert electrical power from sunlight by means of its solar panels and send back a constant stream of signals about its own health and about what it was learning about space. But first it had to survive its ride on the roaring Atlas Agena. Cape Canaveral would be concerned with the liftoff, but Mariner's command center is Spacecraft Flight Operations Center at the Jet Propulsion Laboratory in Pasadena, California. As Atlas carried Mariner out of camera range, contact was maintained through the spacecraft's radio voice. But the following animated sequence demonstrates what was happening in the sky while spacecraft operations plotted the flight on Earth.
Mark 1.
Mark 1, booster cutoff. Mark 2, booster jettison.
Looks like our first marks are right on the nose. Mark 3.
Mark 3, sustainer cutoff. Mark 4, vernier cutoff.
Sustainer cutoff has occurred.
Robert Parks on the right of JPL, who will be keeping Mariner's logbook.
301. Mark 5.
Mark 5, shroud ejection. Mariner's protection through the Earth's atmosphere. Mark 6, Atlas Agena separation. Stage 2 takes over.
What's that coming in from the Cape?
Mark 7.
Mark 7, first Agena ignition.
We have a Mark 8.
Receiving
486 seconds.
Roger, Mark 8, 486 seconds.
Mark 8, first Agena burnout. Now Mariner and Agena go into a parking orbit until the precise moment for the final thrust toward Venus.
Roger, Mark 9, 07 hours, 17 minutes, 43 seconds.
Mark 9, second Agena ignition. Mark 10, second Agena burnout. Mark 11, spacecraft electrical separation. Mark 12, spacecraft separation. Mariner is on its way. The tumbling motion imparted by the rocket's thrust must now be arrested. The solar panels extended. The high-gain antenna moved into position so that communications with its captains on Earth may begin. Then Mariner must get its bearings. First, from the omnidirectional antenna at the top of the spacecraft, which seeks out the sun.
Sun acquisition occurs at launch post 60, where the command should occur then.
Having found and locked on the sun, Mariner begins a cruising mode before attempting to lock on the Earth. At this point in the journey, the spacecraft is still so close to our planet that its Earth sensor, which detects the reflected sun's rays, would be blinded. 7 days later, Mariner begins a rolling search with its Earth sensor at the bottom of the spacecraft. A position lock on the Earth is achieved when Mariner sees the less brightly lit surface of our planet. Slowing from its launch speed of 25,000 miles per hour to a cruising speed nearer 7,000 miles per hour, Mariner will henceforth communicate via the large dish-like high-gain antenna, sending to and receiving signals from Goldstone in the California desert, Woomera in Australia, and Johannesburg, South Africa. The journey continues. The shipbuilder and admiral of this mariner's journey is Robert Parks, Planetary Program Director for the Jet Propulsion Laboratory. He explains the problem to producer Jack Beck.
Well, it's a little bit like a duck hunter sitting on a merry-go-round who was trying to shoot at a duck many millions of miles away and having to lead him by about 100 days. To begin with, it's necessary for us to use a trajectory for the spacecraft that will take it almost halfway around the sun. Because of the launch vehicle energy constraints, we have to take a path similar to this one that's showed in the dotted line down here. And that means that we have to launch at a time when the planets are in their proper relative position, for example, Venus here and Earth up here, such that Venus will arrive on its trajectory at the same time that the probe would arrive at that trajectory.
Well, now, looking at the paths of the two planets, one is led to wonder why you didn't launch your probe at a time to take advantage of their maximum proximity, which was considerably earlier than indicated here.
Yes, that would require a very high energy trajectory, a much more capable launch vehicle than we now have, so that you could fire almost at this time and drop it directly in toward the orbit of the planet. Actually, under the conditions we have here, the communication distances that we have to contend with are not much greater than those you have on the optimum condition for that. We're pretty lucky on the planet Venus. For this reason, we have to time the launching both as to the period in the years and also the time of day very accurately.
You can't make this launch any day or any month. It has to be made at a specific time.
That's correct. The opportunity to launch at Venus on this type of trajectory comes around only every 19 months when the two planets are in their proper relative orientation.
Mr. Parks, we've been at some pains to try to land instruments on the moon. Why are we choosing just to fly by Venus? Why don't we land on Venus?
The entry problem on Venus is a very difficult one. The approach velocities that you would enter the planet with would be roughly equivalent to those of Apollo or greater. And in addition to that, the atmosphere of Venus is very dense. Therefore, it's a very difficult problem indeed that we're not sure the state of the art is prepared for. In any event, would take a lot of weight for heat protection equipment and was not compatible with the kind of weight that we were able to carry on this early mission.
Well, does the planet Venus have an atmosphere comparable to that of Earth?
Much more dense than that of Earth. The best estimates right now are that the surface density is something like 10 times that of Earth.
When Mariner left on its 180 million mile intercept course for Venus, it had built into its navigational instruments the accumulated knowledge and trial and error of 5,000 years of human effort to chart the sky. To explain how a spacecraft could head for Venus with any hope of getting there, as Mariner travels forward in space, we must travel back in time to tell another story, a flashback into the past from Aristarchus to Cape Canaveral, to describe how the road maps of space on which Mariner would depend came into being. Aristarchus of Samos proclaimed in 200 BC that the sun, not the earth, is the center of our planetary system. But in one of the great ironies of human history, that knowledge was unaccountably lost or ignored for 17 centuries until the European Nicholas Copernic, known as Copernicus, rediscovered this key to understanding and thus made possible the resumption of meaningful scientific investigation about the nature of the universe. Galileo Galilei was the man whose espousal of Copernicus's ideas threatened to shatter the society of his time. Galileo did not invent the telescope, but after he looked through this modest instrument in the year 1609, the world was never the same. If the theories of Copernicus and the mountains on the moon as seen through Galileo's telescope rocked the Middle Ages, man's self-centered view of the universe took a far more devastating blow with the advent of the giant telescopes of the 20th century. Vanity compelled the thought that at least if the Earth were not the center of all things, our solar system must at least be the center of the stellar universe. The last 50 years in the telescopes at Mount Wilson and Mount Palomar have showed us that our sun is a rather small star in a system of perhaps 100 billion stars and about 30,000 light years from the center at that. A light year is the distance light would move in 1 year while traveling at 186,000 miles per second. The telescope which Galileo made and later presented to a grateful Senate of Venice, which promptly doubled his salary at the University of Padua, was, so he wrote, capable of magnifying things about 30 times. But the astronomer with his eye pressed to the skyward pointing lens has been replaced in our century by space photography. And the magnifying lens, ground by the spectacle makers of the Middle Ages, have been replaced by giant mirrors which gather light on photographic plates, light which left its sources on the heavens billions of years ago on its journey to this tiny corner of the universe. The most famous of man's optical tools for measuring the universe is the 200-inch telescope atop 6,000-foot Mount Palomar in California. This instrument is approximately 100 feet high and weighs more than 500 tons. Yet it is made with the precision of a watch. So delicately balanced is the entire apparatus that a small electric motor of 1/12 horsepower turns this great weight on its oil bearings in parity with the Earth's daily motion. At the base of a 60-foot column is the world-famous 200-inch mirror. This highly polished surface does not magnify the stars as did Galileo's telescope. Instead, it catches the incoming rays of light from the stars and reflects them back to a focal point where they can be photographed for study and analysis. The bigger the mirror, the greater the amount of light it can collect from greater distances in space. These pictures were made in the daylight when astronomers normally are asleep. In the dark of the moon, when most observing is done, the astronomer rides this elevator up and along the curved inside wall of the dome until he can step off the elevator and over into the observer's cage 60 feet above the mirror. The mirror gathers the light and passes it around the observer's cage to a focal point and thence to the photographic plate in front of the observer. If your own camera were to try to produce the same result, it would need a lens 500 feet long. In addition to taking pictures of stars and galaxies, the telescope is used to make spectrographic studies of the light from them. An instrument called the spectrograph is placed at the focus of the telescope, and the light from the object in the sky is passed through it, separating into the colors of the rainbow. The real work of astronomy is not done on the mountaintops, but in the laboratory miles away on machines which display the light spectrum for analysis. These colors are separated by dark lines, and it is from these lines, their combination, their intensity and position, that astronomers can learn what stars are made of, their temperature, pressure, and magnetic field. What telescopes like the Big Eye of Palomar have discovered and what they see is described by one of the ranking astronomers of the 20th century, Professor Fred Hoyle of Cambridge University.
The Milky Way is only a small bit of a great disc-shaped system of gas and stars that's turning in space like a great wheel. The diameter of the disk is about 60,000 light years. This distance is so colossal that there's been only time for the disk to turn round about 75 times since the oldest stars were born, about 15,000 million years ago. And this is in spite of the tremendous speed of about 500,000 miles an hour at which the outer parts of the disk are moving. The sun and our planets lie together near the edge of our galaxy, as this huge disk is called. By looking at any part of the sky that's distant from the Milky Way, you can see right out of the disk that forms our galaxy. What lies out there? Not just scattered stars by themselves, but in every direction space is strewn with whole galaxies, each one like our own. Most of these other galaxies, or extragalactic nebulae as astronomers often call them, are too faint to be seen with the naked eye, but vast numbers of them can be observed with a powerful telescope. When I say that these other galaxies are similar to our galaxy, I don't mean that they're exactly alike. Some are smaller than ours, Others aren't disc-shaped, but nearly spherical in form. The basic similarity is that they're all enormous clouds of gas and stars, each one with anything from 100 million to 100,000 million or so members. And one of the nearest of them, only about 2.5 million light years away, seems to be practically a twin of our galaxy. You can see it for yourself by looking in the constellation of Andromeda. With the naked eye, it appears as a vague blur, but with a powerful telescope, it shows up as one of the most impressive of all astronomical objects. If truth be known, I expect that in many places there, living creatures are looking out across space at our galaxy. They must be seeing much the same spectacle as we see when we look at their galaxy. It'd be possible to say a great deal about all these other galaxies, how they're spinning round like our own, how their brightest stars are supergiants, just like those of our galaxy, and how in those where supergiants are common, wonderful spiral patterns are found. The Whirlpool galaxy M51, a good example of spiral structure. Notice how one of the arms extends as a bridge to an outlying system. The Horsehead Nebula. The Horse's Head is a cold cloud of gas and opaque dust that's being squeezed by hot surrounding gas.
Space probes have to await vastly more powerful booster rockets than we have now before man can contemplate exploring the planets of neighboring constellations light years away. But the exploration of Venus and Mars are the first tiny steps. If Andromeda is the twin of our Milky Way galaxy, Venus is our sister in the solar family, most closely resembling us in size, mass, and density. Venus is a little smaller than Earth, 7,700 miles in diameter to Earth's 7,900, and it has a surface only 5% smaller than our planet. None of the other planets approaches so close to us. Mercury is nearest the Sun. Then Venus in an orbit that brings it quite close to Earth, which is accompanied on its 365-day journey by its satellite, the Moon. Then Mars. The Venusian year is only 225 days because its orbital path around the Sun is shorter and faster than Earth's. When furthest away, Venus is 160 million miles. When nearest, 26 million miles from us. Because of these changing distances, Venus is a good target for rocket probes only every 19 months. When it is nearest to us, Venus may sometimes be seen with the naked eye in daylight, and it is constantly mistaken for a flying saucer or enemy aircraft in wartime. Morning star, evening star, it has phases of brightness like our moon and reflects 65% of the sun's rays. But for all of Venus's similarities to Earth, it remains a mystery to the scientific eyes which roam the skies, a disappointment to those who turn their telescopes on her, for there are no definite markings to be seen, only shadings, and those rarely. Venus, therefore, is thought to be covered with a permanent cloud layer, and her atmosphere so hazy that the sun cannot penetrate to the surface and out again. Mars never gets any closer than 36 million miles to Earth, is little more than half as big, weighs 1/10 as much. Yet it has yielded to the astronomer's probing eye and camera. Here is a telescopic photo made with ultraviolet light in which surface features are as obscured as they are on Venus. When infrared film was used, here is what astronomers were able to see of the Martian surface. The detail is sometimes even more sharply defined when there is a sudden clearing in the Earth's murky atmosphere. Here on the left is an observer's sketch based on what he saw during such a momentary period as compared to what usually may be photographed, shown on the right. In this remarkable photo, taken by Dr. Robert Richardson in 1954, there is evident a pattern of lines in the form of a W, the sort of phenomena sometimes visible on Mars, which has led to speculation about canal systems built by intelligent beings and has inspired astronomical artists to visualize a surface like this drawing. Although infrared photography has given us exciting suggestions of some form of life on Mars, this technique has failed to give us a view of Venusian surface features. Scientists and artists have speculated that a torrid windswept surface at 500 to 600 degrees Fahrenheit may create a scene like this. Or in an atmosphere of permanent Stygian gloom, the planet is a vast swampland similar to that of Earth in the days of the dinosaur and brontosaurus. While most current evidence tends to support the theory of the desert-like nature, that atmospheric veil of modesty which guards Venus's secrets is also a limiting factor in the kind of vehicles which may be sent there. 9 days after launch, Mariner was to encounter one of the most critical portions of its journey. As hurled into space by the Atlas Agena, its trajectory would have caused it to miss the target area of Venus by 233,000 miles. This had been foreseen, and a small rocket motor had been built into the spacecraft to provide the needed course correction. But before Mariner could be nudged back onto course, a complex set of directions had to be sent to it. Goldstone, California was the scene of the delicate mid-course maneuver carried out on the afternoon of September 4th.
Mark, SC-1 initiated at 21:30:00. SC-1 initiated 21:30:00.
SC-1, the spacecraft initiated 21:30.
At the command console, this tape activated the radio instructions to Mariner.
Correct. And is being prepared for transmission. SC-1 is being transmitted. Being transmitted. Roger. It's going out.
Right.
Looks good.
Looks good.
All systems in sync.
The various instructions of the command sequence are transmitted to Mariner, now 1.5 million miles in space, to be stored and later transmitted back to Earth for verification.
Mark, SC-2 initiated at 21:35.
SC-2
initiated down at 21:35.
After the instruction sequence was complete and Mariner knew what it was to do, the critical moment was at hand. RTC-6 is Mariner's instruction to execute its stored commands.
Mark, RTC-6 initiated at 22:49:00. Command was ready and correct.
Mid-course command has been initiated.
Vehicle is in sync. We still have ground sync. Right on the button. Command is now being transmitted. Going out.
Roger. Going out.
Command now being transmitted.
First command, SC-1. Roll 9 degrees and move high-gain antenna from path of mid-course motor exhaust.
The roll maneuver of the spacecraft has been completed. The roll maneuver of the spacecraft has been completed at this time.
Next, SC-2. Alter spacecraft pitch to conform to new course. SC-3. Fire rocket motor for 28 seconds. 50 pounds of thrust generated by this small motor would not move a bicycle very far on Earth. But in the vacuum of space, where there is no air nor sound, 50 pounds is enough to do the job.
Jack says get the beer ready for him. 130.
Now Mariner must reorient itself on its new course. First, reacquire the sun on the Omni antenna at the top of the spacecraft. Now a searching roll while the Earth sensor seeks the sun's reflected light from the Earth.
There we go. Earth sensor shows a 91.
Good enough.
Finally, locked on the sun and Earth, again Mariner continues its multi-million-mile journey, with the Earth a pinpoint of light below in the blackness of space.
JPL reports that the mid-course maneuver was successfully completed. JPL reports that the mid-course maneuver was successfully completed.
No unusual events, routine Venus probe mid-course maneuver. The sum-up line on a great engineering feat, and as good a line as this correspondent has ever heard for a mid-program break. The story of Mariner continues after this message.
CBS reports 109 Days to Venus continues. Here again is Walter Cronkite.
On September 8th, between 8 and 9 a.m. Eastern Standard Time, Mariner lost position for 3 minutes before making an automatic recovery. Bob Parks reports.
A few days ago, Mariner responded to a disturbance in its attitude. By this we mean the axis toward the sun and the Earth was disturbed slightly. This was not entirely unexpected since we had designed it for such an occasion if it in fact were hit by a micrometeorite. It returned to its proper orientation in a very short period of time, about 3 minutes, and has not had any bad effects on its flight at all.
On September 19th, Mariner made its escape from the Earth's gravitational pull. 4 million miles out from Earth, the sun's gravitational attraction becomes stronger. From here on, Mariner's speed would be accelerated. The spacecraft's account of its exploration was being recorded on giant receiving antennae like this dish at Goldstone. But instruments like it are also part of the space research tools which will complement what Mariner is doing. With the 200-inch optical telescope, man had about reached the limit of his power to see, 1 billion light years into space. But in 1932, Karl Jansky, a communications laboratory engineer, built this crude antenna and revolutionized man's capacity to explore the universe once more. Jansky was merely looking for the cause of radio interference with transatlantic phone calls. What he discovered was the new science of radio astronomy. Perhaps the most striking example of how radio astronomy has complemented the optical telescopes may be illustrated in the case of a radio source which astronomers call 3C295. Radio telescopes at Big Pine and Cambridge, England, had detected a source of strong radio emissions at a place in the sky where optical telescopes had seen nothing. Giving the exact position, radio astronomers suggested that the big eye of Palomar expose its photographic plates for a very long period, although nothing appeared in view. When they did, observers at Palomar were able to confirm with accumulated minute light waves what the electromagnetic waves had suggested: the most distant cluster of galaxies, or possibly galaxies in collision, yet discovered by man. The great instrument at Jodrell Bank near Manchester, England, which grew out of Jansky's discovery, could pick up and complement what had been done with optical telescopes by penetrating vastly greater distances, 10 billion light years, to the very edge of the observable universe. This, the first really large instrument, 250 feet in diameter, and key to many discoveries of the staff headed by Sir Bernard Lovell. The twin 90-foot dishes at Big Pine, California, operated by Caltech for the Office of Naval Research. The new 210-foot telescope in New South Wales, Australia, the only such instrument now in the Earth's southern hemisphere. The 150-foot antenna completed last spring at Stanford University. And now dedicated in the past 6 weeks, the largest radio telescope in the world, the 300-foot instrument of the National Radio Astronomy Laboratory at Green Bank, West Virginia, a dish so large that a football field could be put within its perimeters. Telescopes, whether looking for light or radio waves in space, appear to turn their heads like fantastic metal flowers in search of the sun, as shown in this photograph, which has been accelerated to compress the instrument's movement. The fact is, however, that, as in this night picture of the dishes at Big Pine, California, the telescope is rigidly fixed on radio source 3C295 near the North Star. What is moving is the Earth to which the telescope is fastened. The instrument remains fixed on its target as the Earth revolves. But if man has used his ears to go where his eyes could not, it may be that he has reached a realm where even further advances in technology will not help. Sir Bernard Lovell, a pioneer in radio astronomy and architect of the telescope at Jodrell Bank, explains why.
There is a finite end to what it will be possible to see or hear with the radio telescopes. And this arises because of a very simple fact, namely that these distant objects which are photographed or which are recorded in the radio telescopes are moving away from us at very great speeds because the universe is expanding. And the most distant source recognized at the present time, the cluster in Bootes, as I've just mentioned, is moving away with a speed of something like 80,000 miles per second, nearly half of the speed of light. And out to this greatest distance which we've so far penetrated, the further we penetrate, so the greater is the speed of recession. It still seems to be increasing linearly with distance. And as we approach the speed of light, so we begin to reach the ultimate limit at which it will be possible to observe the universe. The classic phrase used by Eddington, that light is like a runner on an expanding track, that as he approaches the winning post, so it recedes ever further from him. And this is precisely the situation which I think that we are now and probably have reached with the work which is going on with this telescope at the present time.
Man's sharpened ears for listening to deep space have raised other interesting possibilities. One of these is that we may not be alone in the universe, that we may be part of evolving life patterns scattered throughout space, some of whom are far more advanced technically than are we. If there is some intelligence to be found elsewhere in the universe, how do we contact it? A man who has thought about this problem is Stanford University's professor of astronomy, Dr. Ronald Bracewell.
Well, we can mention a very interesting principle here. If we go out trying to communicate with other forms of life, it's almost certain that what we find will be something inferior to ourselves. For instance, when Columbus crossed the Atlantic to look for he was looking for China, I believe, what he found was a race of people that were inferior. Now, of course, this must necessarily have been so, because if there had been a civilization more advanced than the European located in America, then they would have discovered Europe. We would have been in the position of being discovered. Likewise, when we go out into our own solar system, as is already being done, and investigate the planet Mars, for instance, all we expect to find is vegetables. If there was any community there with control over firing rockets, modern technology, then they'd be down here finding us. So the answer to your question is that we are not going to go out and find this advanced life. It's going to come and find us.
Well, do you think it likely that within the limits of our solar system there may be such probes ranging around now?
Well, there could be. It's a suggestion. If they're going to leave some sign here of their existence, then one very good way and one cheap way of making a conspicuous sign would be simply to lob a radio transmitter into orbit around our sun, which would use solar batteries to keep its power up, and it could run on for hundreds of years, making a quite conspicuous signal and indicating to us that someone had been there.
If some extraterrestrial Kilroy has been here, there's no evidence of it yet. But for the first time, a search is underway. An astronomer who already has led an effort to establish such communications is Dr. Frank Drake, Chief of Operations for the new 300-foot telescope at Green Bank, West Virginia, who talked with Jack Beck.
Doctor, there's an awful lot of space. How do we know which frequencies to tune to?
Well, that's a very interesting problem, and one for which we don't really have a good answer yet. If you want to, you can look at it this way. We're trying to meet someone in New York City. But we don't have an opportunity to arrange with them in advance where we're going to meet them. Now, what would you do in a case like that? Well, you don't go just stand on the corner of 5th and Canal Street or something. You go stand someplace that's very important, that you consider important, and that you know the other fellow considers important. And that means we have to know or guess what other civilizations may know, and that's both difficult and dangerous. Now, we do have in space a few places such as Grand Central Station or Times Square, places that most everybody will know about. These are special frequencies which are of a special importance to science. One is the frequency on which the hydrogen of space, the basic building block of the universe, transmits radio waves, the frequency of 1420 megacycles. Perhaps that's the place to stand and wait. And in fact, that's where Project Ozma operated.
Now, what do you surmise might be the content of such an interstellar message?
The first message should actually start carrying useful information. Now, one way that seems particularly appealing, because it can be decoded immediately without either side having a common language, is a television picture. A television picture could be decoded immediately by anyone on Earth.
Now, when you're talking about television pictures, you're not talking about Gunsmoke or I Love Lucy. You're talking about something much more abstruse, I gather.
Yes, these pictures are much more abstract. They, in fact, are only black on white, and I think to the ordinary television viewer, they would look very crude indeed. I have one example here. This is the decoded picture, and this is it. And of course, at first sight, it's a pretty ghastly thing. Now, this picture contains what we would consider the most important first things to know about another civilization. For instance, we want to know what kind of creature we are dealing with. And here you see a sketch of the creature. You see it's a primate like ourselves, a little stockier, and it carries its legs sort of outboard. Maybe it even has a pointed head, but not much different from ourselves. Another thing we want to know is what kind of planetary system it lives in. And here we see a schematic diagram of a planetary system with the central star, 4 small planets, an intermediate-sized planet, 2 giant planets, an intermediate-sized planet, and a small planet.
Dr. Drake, portions of what Mariner is now doing on its way to Venus, or is going to do when it gets to Venus, grew out of radio astronomy. Can instruments like this one still contribute now that we're sending probes out into space?
Yes, instruments like this can still contribute a great deal. In fact, they complement the work of Mariner. And many of these instruments, including this one, are observing Venus right now. They are able to observe on frequencies other than the Mariner frequencies. They're able to observe Venus over long periods of time. All of this information added to the Mariner information will give us a very complete picture of the phenomenon existing on Venus.
On the 31st of October, on the 65th day of flight, there was a very sudden change in the voltages and the currents that are being measured coming from the solar panels that supply all the power to the spacecraft. The voltage dropped, and the currents indicated that we were getting power only from one solar panel. After about a week of observing the spacecraft, the solar panels actually returned to their normal operation, the voltages and currents.
CBS reports 109 Days to Venus continues after this message. Here again is Walter Cronkite.
In less than 48 hours, the 2 stories we have recounted here, man's search for knowledge about the universe and Mariner's probe of interplanetary space, will come together in a point of time. The drama will take place at the Space Flight Operations Center at JPL in Pasadena. We talked there with Bob Parks as the tension mounted. Mr. Parks, we've been talking about months and then weeks and now days in Mariner's journey to Venus. At one point, after launch, you didn't know whether you had a spacecraft, and we didn't know whether we had a television program. It's been a very long wait. What's it been like out there?
Oh, man, this has been a real experience for all of us out here at the laboratory. Many of us had gotten used over the years to the tremendous tension, nervous tension that builds up for a rocket launching. But in those cases, it was all over except for looking at the data in, say, 10, 15, 20 minutes. In a shot like this, where you maintain the same level of tension over 3.5 months, it's been a real experience, as I say. You are having to watch the spacecraft continuously, interpret all the data that's coming back from it and all the changes in this data, the indications that they might have. And, of course, in the early part of the flight, you recognize how long we have yet to proceed along this mission toward our objective. And now when we're getting down to the very last few days of the operation, the tension is really mounting here because we are approaching so close to the objective that we've all been aiming at.
Well, now we're down to the last 48 hours before encounter. And how does it look? Are we going to make it?
Well, we wish we really knew the answer to that question. Every day we get closer gives us more confidence that we will make it all right. There are some things on board the spacecraft that we won't really know are going to be operational that are important to the actual encounter data that we won't find out for some time. The thing that has us worried the most at the present time right now, of course, is the high temperatures on board the spacecraft. They are considerably higher than we anticipated, and either above in some cases or in the neighborhood of the upper operational temperature limits of some of the equipment.
And what's your best estimate at this late hour as to how close Mariner is actually going to come to Venus?
Our estimates are still falling consistently at about 21,000 miles from the surface at the point of closest approach. We still have some uncertainty in that figure of a few thousand miles. We'll be able to get a much better indication of this if we can actually get good tracking data during the pass by Venus, because we're able to see how it's perturbed by Venus itself, and this will give us a much better point on the information with regard to just how close we did come.
What exactly will Mariner do, Mr. Parks, as she approaches Venus, and then how long will she be scanning Venus's surface?
Well, the first thing that happens, about 10 hours prior to the closest approach of Venus, we go into what we call the encounter mode. This does two things. First, it starts the scan motion of the two instruments. During this period of time, we'll begin to get data from the vicinity of the planet Venus on through the entire counter period on such things as, is there a magnetic field of Venus? Is there a Van Allen belt? Are there radiation particles around the planet Venus? Is there any concentration of micrometeorite dust around the planet? Actually, then the two instruments that scan the surface of the planet will first see the planet at about 1:55 Eastern Standard Time. It will see the dark side of the planet first on the trajectory that we're on, and then we'll move on, and at about 2:16, it will be observing the point on the planet where the sun is setting on the planet.
Mr. Parks, what do we expect to learn from Mariner that could give us a clue as to the possibility of life on Venus?
Well, of course, one of the big purposes of the experiments we have on board there is to tell us the surface temperatures of the planet Venus. Now, of course, if we can confirm the fact that the surface temperature is up in these very high temperature regions, it almost precludes any life forms, at least as we know them here on Earth, from existing on Venus. Now, in addition, the information we're trying to get is whether or not some indication of the water vapor content in the clouds of Venus, whether or not there are holes in the clouds on Venus. The pictures we're able to take from Earth would indicate that there are none, but we can't get fine grain pictures here, and these instruments could tell us whether there are any holes in it and whether they penetrate all the way to the surface or just they're through several layers of the clouds, and information of that type.
What have we learned so far about the space between Earth and Venus from Mariner's interplanetary journey?
We received such information, for example, as the fact that the cosmic dust out in deep space is maybe 1,000 or 10,000 times as less dense as it is around the Earth. For example, measurements made by Earth satellites. We've received a lot of information on the solar wind, the relatively low energy particles that are boiling off the sun and radiating outward from the sun. We've received a lot of information on the magnetic fields out into space.
Mr. Parks, if Mariner's communication system failed today, would Mariner's trip still have been worthwhile?
The accomplishments of Mariner 2 to date have actually been of tremendous significance, both from the standpoint of the scientific data that's been obtained back from interplanetary space and the regions between the Earth and Venus, the type of environment that will exist out there, particularly as it pertains, for example, to whether man can exist out there, what protection he will have to have, from understanding the basic physics of the sun and the solar system and the things that are taking place out there. We have data that I think can keep the scientists busy for many years in interpreting and adding to the basic understanding of the physical phenomena taking place out in space. In addition, we've received a tremendous amount of data and experience pertinent to the operation of the engineering equipment out in this environment, the long lifetimes involved, the temperatures involved, and how to control these temperatures, the communications over distances of the order of 30 million miles or more with very low power. The operation of all the equipment, the attitude control and so on, has been of tremendous value in leading and telling us the way to proceed in the future exploration of space that is planned.
What will you be doing out there at the Spacecraft Operations Center as Mariner flies by Venus?
We'll, of course, be having a very close watch on the operations. We'll be standing by observing the data as we get it and being standing by to take any emergency operations that appear to be warranted or that we are capable of here.
What's going to become of Mariner after she flies by Venus?
Well, it'll go into an orbit around the sun, and the exact orbit will be a function of precisely where it goes by the planet Venus, because it'll be perturbed very much by the gravity effect of the planet Venus as it goes by. We know that this will put us in a trajectory that will go back outside of Earth's orbit, and will cross Earth's orbit twice.
Well, Mr. Parks, how long after the actual flyby are we going to get the answers to the many questions that to which we're seeking the answers? How long is it going to take to compile all the data? Days, weeks, months, what?
I think we have data here that people can work on for many years to come and really refine it. But to get the first real significant implications of this data, I think we can obtain in the order of months.
Well, good luck to all of you out at JPL. We'll all be watching.
Thank you.
Mariner 2 already has established itself as man's most successful probe of deep space. And now, if luck holds, in 2 days we'll begin to get the answers to questions that have troubled man since before Aristotle. There is a point of view in the scientific community that while manned adventures like a landing on the moon are certainly more glamorous and exciting, the space race will go to that nation and explorer who first brings back evidence that there is life elsewhere in this universe. Mariner's 109 Days to Venus and the Soviet Union's black box now on the way to Mars certainly will add new pages to the road maps of space, and perhaps will give man a preview of the places to which he now seems determined to go. On my regular news program on Friday night, we hope to be able to give you the final account of Mariner's remarkable journey. Good night.
CBS Reports, 109 Days to Venus, was filmed and edited by the staff of CBS Reports under the supervision and control of CBS News.